All right, I'm Ben Jarvis. I'm the lead storage architect on Myriad, and we'll talk about the architecture of the system and the path we took to get here. All right, so Myriad had sort of presented us with an opportunity to take the experience that the team had doing high performance video and HPC workloads and start with a blank piece of paper and build a new system. And in doing that, we wanted to take advantage of several concepts. The main one being that we wanted to adopt the paradigm that has evolved for large scale out internet facing services. So if you're running a video streaming platform or a rideshare service, there's a paradigm that people adopt in order to scale out those services effectively, usually running in a public cloud. And we wanted to take those concepts and apply them to a storage product, whereas typically storage products have much more old-fashioned scale-out models involving high availability and failover and things of that sort. So we built Myriad as a microservice container-based system. So all of the components are all containers, and all those containers run in Kubernetes. So we present, file and object protocols on top of a file system stack, have internal data services all running in containers, all running on Kubernetes, and then that Kubernetes platform then runs on a sort of cloud style white box commodity hardware platform. So the system is a redirected write system. It does inline data protection with mirroring and erasure encoding. We do data reduction, both compression and deduplication inside the stack. And then that entire thing is sort of presented as a self-contained cluster to the customer. Additionally, we wanted to build this system on the assumption that the storage is always NVMe flash and the network is always a high performance RDMA Ethernet network. And the reason for that, frankly, is because a modern storage server full of NVMe drives and with 100 gig or 200 gig Ethernet connections can perform at a hardware level at 100 gigabytes per second or more, or tens of millions of IOPS. And therefore, the problem in building a scale-out storage system is no longer how do we efficiently use IOPS in order to avoid wasting them. Rather, it's how do we make the software light enough and flexible enough that it's even possible to use all of the storage performance that the hardware can provide. So it sort of inverts the model from what you traditionally do, whereas, for the last 30 years, storage systems were all built around trying to avoid talking over the network, trying to avoid using doing IO operations to the storage as much as possible. Whereas now the design really should be centered around optimizing for memory bandwidth and avoiding context switches and that sort of thing, so that your software is able to run at the speed that the hardware wants to run at. So we took all of those things in combination sort of to build this system with those priorities in mind. So I'll stop there if there's any questions.
Yeah, a little bit. Around the Kubernetes, I'm trying to understand in my own brain a bit where the Kubernetes cluster and its own state management stuff ends and where the state management for your system begins, because the state needs to be stored somewhere. Could you explain a little bit how that works with the actual physical storage that lives on the nodes?
Yeah. So we have a Kubernetes cluster. Let's say it has 5 nodes in it, and Kubernetes has its own raft system and its own control plane, usually etc.d, which is what we're using. And that's in charge of maintaining the state for Kubernetes, like which containers are running where, which containers are part of a set that is exposed as a service, making sure that the network is pointing those service IP addresses at the right set of pods and that those pods are running, that sort of thing. And then we are running our system inside containers in that framework, but we have our own state management directly on the storage. So a Myriad system uses VFIO to talk directly to NVMe drives, either locally or in another node with Rocky. And we store all of our state essentially on the hot swappable U.2 drives in the node, while Kubernetes stores its state on the root drive of the node using etcd. So we do our own data protection and our own, rebuilding when nodes go down and whatnot, but that all is sort of orchestrated by Kubernetes. So if it sort of makes sense, Kubernetes protects the availability of the service while we protect the data that's in the system.
Gotcha. So Kubernetes is the control plane for your software, which is in containers, which are just like processors. And those run on compute nodes somewhere in the Kubernetes cluster, but the Kubernetes is just there to make sure that your software is running. The actual system is all your software running in containers, which you could do anyway without Kubernetes, but then you need some sort of mechanism to coordinate all those bits of software. So what you're saying is instead of writing one yourselves, you'll just use it. Well, Kubernetes is there. It's what everybody else uses. We'll just use that.
Exactly, yes.
Do you have any pushback from, let's say, more legacy workloads when you say you need to move to object storage from block? It's a challenge I've been seeing a lot with the workloads that I deal with.
Not so much specifically that, because the object store we're using is sort of internal business of the system. So you can pretend it's not there as a customer if you want to. We're sort of secretly implementing a file system on top of the object store, and I'll get to that in a subsequent slide in more detail. But we do get some pushback just in the sense that our system is shaped like a cloud Kubernetes deployment and not like a legacy storage system. So there is a little bit of getting your head around that we've gone through with customers, and we'll get into that.
Interesting.
All right, so in addition to using Kubernetes and whatnot for the software management, we're also running on white box hardware. So that means our compute nodes are just 1U servers full of NVMe drives with high-speed Ethernet cards. There's no proprietary cache hardware or any dual-ported drives or anything like that. It's all just off-the-shelf stuff. And our network switches are also white box switches, running open source Linux software. Of the sort that you would use if you were a hyperscaler building a public cloud. And one of the characteristics that Kubernetes has is that while it does all of this service orchestration and control plane stuff for you, the networking for that is fairly complicated. And we didn't, if you're using a public cloud, that's not your problem. The public cloud does that for you. But if we're going to deploy this in, an on-premise data center, we don't want to expose that complexity to the customer. So we built Myriad essentially as a self-contained cloud cluster that you deploy in your own data center. So that starts with what we call the deployment node, which is just a 1 gig management switch running some software that we wrote on it. And that orchestrates the provisioning of the rest of the hardware. So you rack your deployment node, you log into it, you configure the external networking settings and whatnot that you want, and then you just plug in all the other hardware and turn it on, and the rest of it all just automatically sorts itself out. So all the internal networking is a fixed known configuration that's the same in every install. That means that all of the priority flow control and RDMA stuff that's needed for the RDMA to work smoothly inside the cluster is not exposed to the end user. And then what the end user is asked to do is just peer their network to our external load balancer nodes, which are not only 100 gig switches. So we essentially have a layer 3 peering relationship with the customer network rather than a layer 2 presentation with like VIPs. And that has the attraction that if this cluster were, say, 1,000 nodes, you can still address the entire thing from the customer viewpoint with a single IP address. As you would go to, google.com to do a search and not have to care how exactly that request is being honored on the back end. So that, going back to the prior question about, sort of pushback about doing things differently, we do see some, hesitation to do that because it's a new thing in a storage world. But I think when people try it and understand it, and especially as they scale it, the fact that they can, go into their data center, hook up some new nodes, turn them on and walk away and be done, in the same sense that you push a button and make an instance in EC2 is attractive. So.
One question, you mentioned the load balancer, you say that they are just switches with software on this to orchestrate. what are the load balancer and how can you ensure that they do not become the bottleneck of your solution?
Yeah, I mean, the load balancer nodes are just 100 gigabit switches running Sonic, which was developed by Microsoft for Azure. And it's a sort of vendor neutral platform, meaning we can, in theory, source switches from lots of different people and run the same software stack on them. We run them redundantly, so there's at least two of those switches, and they essentially function as leaf switches in a class network. But with the added extra bit that since we can, we also run some of our own lightweight software on them to manage things like internal DNS in the cluster and DHCP and that sort of stuff. But while still preserving to the outside that it's just a BGP peering relationship to the customer network. So that we don't worry about them being a bottleneck so much because all they're really doing in the data path is moving packets around in a switch ASIC.
Yeah, you still need the switch to connect, so they are just this. And you mentioned that outside is just one IP. You mentioned that the storage is seen as one single IP, is correct?
Yes. Yeah, it's BGP announced the same IP address from both of those leaf switches, load balancer nodes.
Okay.
The customer would then use ECMP to multipath across. They might have 8 cables going into each of those switches. They might have multiple of their own switches paired with them. That's kind of up to them. But in sort of the normal way the internet works, you somehow set up ECMP routing to get the packets for that IP address into those leaf switches. And then the switches support NAT in the hardware. So they then translate that IP address into the internal Kubernetes IP addresses, because in a 1,000-node Myriad cluster, you might have tens of thousands of internal IP addresses that Kubernetes is managing. But that's all automated and internal to the cluster, not something that the end user has to concern themselves with.
Very cool. Thank you.
Okay, so like we sort of alluded to, Myriad fundamentally at its heart is a transactional key value store. And it's transactional because in order to make a POSIX compliant file system, you have to have transactional capability to do things like atomic replacement and rename and whatnot. So a sort of truly embarrassingly parallel object store cannot be used, at least by itself, to make a file system. So we built our own key value store that supports transactions while trying to stay as lightweight and close to the hardware as we can, so that it's high performance. We get high performance out of it at small object sizes. So Myriad really, again, is a key value store that we use to build a file system. So the Myriad file system, the inodes, directory entries, and the extensive data in the files are just stored as objects in the object store, and the object store does the heavy lifting, which means our data reduction and our data protection all are features of the key value store, and the manner in which we handle the transactions of that is sort of the part of the IP of the product. And that's really where the aspect about being built for flash and being built for high-speed networking comes to the forefront, because we built it that way on the assumption that what we care about is being able to run as many of these transactions as possible concurrently at low latency, directly driving storage. So the stack from there down is sort of vertically integrated, so that when a given thread in some NAS front-end service container wants to modify the system, say because a file write came in, it talks directly to NVMe drives in the local node and in the other nodes without any other intermediate processes. So if you're thinking about it from a terms of network hops, there's two: one to get from the client into the front-end service protocol container, and another one to get from there to the actual storage device. And the internal hop is always RDMA, since our internal network always supports Rocky, and we always set it up in that way, which allows us to, we've gotten a lot of mileage out of being able to make that assumption in terms of building the rest of the system in a way that is amenable to that.
Less a question and more clarification. I think I understood you correctly that the two hop thing I think is important because it highlights what you've done differently to other options. I mean, fundamentally, every storage system is a key value store at the heart of it. There's a database behind everything. And I've heard a similar sort of pitch from a few other storage companies over the years that they kind of come down to this key value store and where that is and the network path to it. I like that you're highlighting the difference. Like, what have you done differently to other ways of doing this? And to highlight why you would use this, like what have you optimized for? Because I can see that there's some things, again, some more traditional things that this may not be really well optimized for, but that's because you've made specific choices for the kinds of workloads that you're targeting. So it's things that are very low latency and very large scale. Is that an accurate assessment of what you're targeting with this?
Yes, and essentially, yes, we're optimizing for latency and we're optimizing for, if you like, CPU usage per storage operation. And yeah, so typically, like traditionally, you might see storage take the form of a HA disk array with controllers in it, and then you might run a key value stack on top of that, which talks to those disk array controllers. And then you might implement your application such that it then talks to the key value store. And a big part of what we did here was sort of vertically integrate that stack. So that's all just code running in one process. So like our erasure coding is what we call initiator driven, meaning the entity that actually wants to perform the IO is the one that computes the erasure code. And the other end, which just receives that IO, is just a dumb storage target, which is amenable to NVMe OS style operation.
I do have one question related to the way you're handling these, this key value store. Is there any impact here in what you're doing in terms of, the way you handle flash, reads and writes, especially in terms of, managing the flash translation layer? Because we often hear people saying that some of your competitors say that they prefer to use an approach where the FTL is fully managed. So, and here you're using white boxes systems. So is that kind of impacting the efficiency?
Yeah, to an extent. We like running on commodity hardware. I like to leverage the work that the people that make these drives put into them. Maybe I trust them more. But also, and we'll get into this a little bit more, we write all NVMe drives as though they were zone drives, because that's polite to the drive. So I think I would argue that the only time you're going to get a significant benefit from, bypassing the translation layer in Flash or trying to take that on yourself is if what you would otherwise do via the Flash translation layer is not polite to it. So we just try to structure our workloads so that writes in Myriad are always sequential. We'll get into that a little bit more, but it's a redirected write zone-based system. So therefore, we're not forcing the drives to do internal read, modify, write, and unnecessarily consuming endurance that way, and also unnecessarily consuming performance that way. So that helps a lot. But I guess I would say a core tenet of the system is to try to deliver performance without having to depend on hardware magic to do it. So this slide kind of goes over the life of a write in the system, right? So we have some NAS client, and it performs a write to the NAS layer. That is then essentially directly translated into the file system, which is just a library running in that same container. And the file system is essentially just translating the file operation into a transaction that modifies one or more key value objects. And that transaction is then run in the key value store. It's at that stage that data reduction occurs. We compress the data and then we deduplicate it globally. And then that goes into our erasure coding system, which essentially we have a cluster of 5 nodes. Each node has 10 drives, say, so there's 50 drives. We break those drives down into zones of the same fixed size logically. And then we erasure code across what we call a zone set, which is just a zone chosen from a different drive in a different node, such that the failure domain allows us to remove an entire node worth of drives or 2 nodes worth of drives and still recover the data. So the erasure coding is vertical, if you like, across nodes rather than horizontal within nodes. And it's also randomized in the layout so that, whereas in a traditional RAID, the first block of drive 1 would be protected by the first block of drive 2 and so on. We intentionally randomize our zone sets across zones in different drives so that we avoid hotspots in content and so that we can utilize the full bandwidth of the cluster when we need to do a rebuild to recover data. So if you pull one drive out and replace it with a blank one, since all of the content you lost on that drive was part of zone sets that have their other members on all of the other drives, we can use the full read bandwidth of the cluster to access the, to regenerate the data we need to put on the replacement drive, which, at some level is unnecessary because you can only write that one drive so fast anyway. But what it means is we're not making a read performance hotspot on other drives while we do the rebuild. That's sort of evenly distributed, which means the hiccup you see in performance as a result of doing that is reduced. And that kind of thinking, frankly, on this team comes from our heritage doing video production stuff and wanting to avoid performance hiccups causing drop frames and whatnot. So we view performance not just about how many gigabytes per second can you do or how many IOPS can you do, but how tight are the bounds between the best and the worst case you might get in any given 10-second interval as the system is operating. So
what's a kind of typical rebuild time for doing those sorts of drive swap operations or even a node swap operation?
They're about the same, 10-15 minutes. It depends on, it basically just comes down to how long does it take to write the full content of a drive. And then if you do all the drives in a node at the same time, then it's just, we do them all in parallel. So it's fairly quick.
What about the size of those ranges? You segmented an object in multiple objects, but is a fixed size or what's the choice of this?
Sure. We cap the size at a megabyte for an extent of a file, and they can be smaller than that. Obviously, it depends somewhat on the way the file was written by the client and also how our data reduction is handling it internal. So the system is a very variable size design. Also, we compress all of the data. So even if a client were giving us 1 meg sequential writes, if the data is reducible, they're not going to be 1 megabyte anymore after we compress them. They're going to be random lengths. So we just end-to-end concatenate those together as we flush them out. And and the data reduction is essentially just looking for objects where the value side is the same, so that we only store each unique value in the key value store once. All right, so this picture gives a little bit more detail on how the zone sets are constructed. So you can kind of see each node consists of different zones, and then a zone set is randomly built out of those different zones. The zone sets can be either mirrored or erasure coded. We use mirroring for metadata and erasure coding for data. Data meaning user data, i.e. the contents of files. The erasure coding is, handwritten stuff we did ourselves that, again, is baked into the initiator. So when a NAS front end runs a transaction, that transaction generates some set of new content. That content is logically placed into these zone sets and then written so that each entity in the system can be doing that in parallel into different zone sets at the same time. Obviously, doing that on hard drives would be madness because you're intentionally taking on random I/O, but since it's flash, we don't care, and it works fine. We nominally use a +2 erasure encoding. but we could go higher if we wanted, or lower if you were feeling lucky. We use +2 so that we can have one of our nodes in a cluster down for maintenance and then still handle the failure of another node while that's happening. Obviously, if you increase the protection beyond 2, then your effective usable space becomes less. The system gets more efficient with scale, because if you have a 5-node cluster, you're essentially doing 3 + 2 erasure encoding. If you have a 10-node cluster, it's 8 + 2. In order to avoid having failure domains that are too big, we stop at 16 + 2. So if you had an 18-node cluster, you've sort of topped out at your usable space ratio. But then as you add more nodes, since the zone sets are randomized, you still maintain that efficiency as you add more nodes. So if you had 30 nodes, all of your data would still be in 18 + 2 zone sets, but the zones in those zone sets would be randomly distributed over your 30 nodes. Okay, and then the last piece of this is our transactional system, which is, I would argue, the most important piece of IP in the system. And that's essentially comes down to, how do you maintain coherency in a large distributed system at these levels of performance? The traditional approach is some kind of distributed shared locking scheme, so that every entity that, say they're going to go modify a directory by putting a new file in it, first has to get a lock on the directory, and then perhaps a lock on storage, and then performs the operation and then reduces the locks. And the problem that that has is it doesn't scale. People like to design things that way because it gets the single bottleneck out of your block diagram of the system, but it doesn't actually remove the bottleneck. It just makes it a distributed phenomenon that happens within the system. And to some extent, that's okay, because to build a transactional system, there is a fundamental need to have a synchronization mechanism, and that will impose some kind of bottleneck. So the trick is just to try to make the scope of that bottleneck as narrow as you can. And the way we do that is with what we call a work at risk approach, which means every thread in every system, every thread in every process in the system that's performing operations on the key value store can operate independently on the presumption that they are not making conflicting modifications with anybody else. So they'll say they get a rename of a file, they'll check in the latest version of the system that they have. If that operation appears to be legal, they'll logically perform the operation, and they'll generate the new content that represents the changes that they made. They'll flush those changes to a zone set. At this point, because the system is redirected right, nobody else knows that this is happening. They haven't written anything that anybody else can see. And then the very last step of the process is they submit what's called a merge request, which is basically saying, I have taken a particular shard of the system and I've modified it in this way, or I've taken these 3 shards and I've modified them. And then all of those merge requests are processed by a service that checks them for conflicts against each other and then approves or denies them. So they're approved if no other conflicting modification happened to the same set of shards in the time frame in which the operation was occurring. And because the number of shards is huge compared to the number of entities writing, the probability of conflicts due to unrelated file system activity is near 0. We're leveraging the fact that a shared file system, while in principle it allows lots of different people to be modifying the same content at the same time, that's not typically how they're used, and most applications don't even work if you do that. So we're trying to optimize for the case that different entities are writing different data to different places at the same time, and not hinder that workflow in favor of the much less common contended workflow. And this scheme, essentially doing the work at risk and then only at the end synchronizing and finding out if it worked or not, is a good approach as long as you succeed almost all the time. Because the entity that has to process these merge requests, while in principle that's still a bottleneck, that's a very easy job that can be done quickly in the CPU cache on some node, as opposed to something that has to operate on the entire corpus of data that's in the system. And it also is the case that as it as the system becomes faster, these conflicts become less probable. As in order to have a conflict, you not only have to modify something at the same time as somebody else, but you have to be doing it at the same time as somebody else. And that doesn't mean that if you modify a file at the same lunch break as somebody else, you're going to have a conflict. It means you modified it in the same 150 microsecond window as somebody else. And the probability of that in practice is low. So that allows the system to scale out in a way that locks tend to cause a gridlock.
Do you have any upper bounds or exhibited ceilings on how far you could take this? My background is in relational databases and infrastructure underneath it. So when we're talking about multi-terabyte databases, I'm curious just how far could we push this with lots of individual components for that database residing on this and making sure that we've got transactional integrity at the database layer?
Sure. With just a single entity doing the merges, you can get into the high hundreds of thousands, low millions of merge requests per second. And then that can be extended further by using a concept we call delegation, which is that instead of each merge request representing like a single original database transaction, if you want to think about it that way, we take a group of, say, 8 transactions, check them for collisions with each other, which could be done anywhere. And then if they don't collide, which they usually won't, that entire group of 8 can then be represented as one merge request, which you can then pass to the entity. So you can sort of focus, large amounts of activity into smaller amounts of activity. And if you take that approach, then in principle, there's still a limit because there's a limit to how deeply you can nest these things before the latency will start to get you. You can scale that approach very high, I think.
That's pretty slick.
Yeah, so if I understand that correctly, you've taken what is kind of a centralized process that is fast and is quite small, and you can turn that into a distributed computing problem by using delegation.
Yes.
But still POSIX compliance. That's cool.
Yeah, because most of what's happening is people aren't writing the same stuff at the same time, and particularly because the kinds of workloads you're targeting, they're very unlikely to need to do that.
Right. Especially over NAS, because it's kind of an act of insanity to do that kind of a workload over a NAS protocol in the first place.
Are there particular workloads that you would want to avoid because they start being more likely to cause this kind of parallel write conflict problem?
Yeah, absolutely. There are very old school HPC workloads that involve things like making a terabyte sparse file and then having every node in the cluster populate a different 512 byte chunk of it. And there's still benchmarks out there that emulate that, and we are not good at those benchmarks. And that does not keep me awake at all anyway, because the only reason people do that is because they have ancient software. I mean, even never mind Myriad, the industry has moved away from that because it has all kinds of problems to some kind of scatter gather kind of methodology. These days people use Hadoop and things like that, which solves that problem before it gets to the storage, so that what the storage sees is just a single writer to any given file at a given time. So we're certainly optimized for one writer at a time per file. And I would just argue that's almost the only use case that matters today.